All right. The most useful tool you have in statistical analysis for two variables is the line of best fit that you can calculate based on your data set. Now, perhaps you've been taking a science class or chemistry, more specifically, maybe a little bit of physics, where you get a bunch of dots on your grid and then you have to put in a line of best fit. And up until now, you've probably taken your ruler, squinted up one eye, and kind of worked it out. And just struck a line through them based on where it felt like it should go. But there's a better way, and we're going to do it now. We're going to actually take the data points, work out the correlation coefficient for a set, and then based on the standard deviations, that will generate a slope for that line of best fit, and then we can use that to work out a Y-intercept for it. And then we'll use the correlation coefficient to decide whether that line is actually a good fit, because it doesn't say the line of good fit, it says the line of best fit. So there's an option there for no lines being good, but this is the best one. So we'll see how that goes. So I have one prepared for you here, but before we do, I just want you to gaze upon the horror that is that title. The least squares regression line of best fit. So deeper in the knicker-knacker of how this works is a reason why it's called the least squares regression. But that's not really important to you. We're only going to do one type of line of best fit, and that's this one. So from this point forward, I'm just going to refer to it as the line of best fit, and you are going to know in the back of your head, oh, he means the least squares regression line of best fit. And we'll call it a day at that. So here we go. You may accuse me of some conspiracy here, and that is fair. But clearly, you can see from this data set, once I get it wedged in there, that the hours you spend studying for data management increase your final grade. So now that we've established that, here are your x values, here are your y values, and you can see that 2 hours studying with a final grade of 80, well, that's here. 12 hours of studying with a final grade of 80, well, that's there. And there's the rest of the data points in between. Now, the first little topic here when you're drawing a line or doing a scatter plot in general is trying to decide what goes on the x-axis and what goes on the y-axis. And so that's usually a matter of some logic. Occasionally it's a matter of some choice. If I were to tell you that we were comparing final grades with hours studying, you'd have to ask yourself, does more time studying have an effect on my grade, or does my grade have an effect on how much time I spend studying? And I think the idea anyway, perhaps I'm biased as an educator, to press upon you is that the more time you spend studying, the better your grades will be. So it's sort of implied here that the hours studying are what caused the effect, so it should go on the x-axis. And the final grade is the outcome that we're going to observe as a consequence of those hours being studied. So anything that is causing the effect goes on the x, and anything that we're observing to have occurred as a result goes on the y. And when you phrase this as describing the graph, you would call this final grades versus hours studying. Notice that this thing here, the first thing that was quoted is the effect, so that's y, versus the cause. So I'm going to go through this and I'm going to do some calculations in order to help calculate the equation of the least squares regression line of best fit on our final grades versus hours of studying graph. Now this is another opportunity for me to use my fast forward button, because you've seen all these calculations before. Basically, I'm going to get a standard deviation of x, a standard deviation of y, a covariance, and a correlation coefficient. And once I've gotten those four quantities, then we'll slow down a little bit and talk about what to do with them. So now that we've gotten to this point, you can see from the correlation coefficient that I just calculated that this data is not well represented by a line. I was hoping to get something up in the 0.8, 0.9 range, and then I could say that this model was in fact linear. If you were to take this number and square it, to quote the R² value, you would get 0.247. So some people read that as 24% linear, or 24% reliable on a linear model. Either way, it's not very good. But we are going to forge ahead just so I can show you how this line shows up on the grid and what we can interpret from it, if we can interpret anything at all. So once we have this correlation coefficient, the next thing we need to work on is the slope of our line of best fit. So there is an equation for that. In order to get the slope, you need to take the correlation coefficient and you need to multiply it by the ratio between the standard deviation of y and the standard deviation of x. So in this particular example, my correlation coefficient of 0.497 multiplied by my standard deviation of y, 9.428, and my standard deviation of x, 3.636. If I work that out, .428 divided by 3.636 times 0.497 gives me 1.289. Lovely. Now, if you remember anything from grade 9, a line requires two quantities. It needs a slope, which we have, and a y-intercept. So the way we get y-intercepts is you have to think all the way back to grade 9 and remember that y equals mx plus b for any linear relationship. M is the slope. X and y are the coordinate pairs that fall on the line of best fit, or on the line in general, and b is the y-intercept. So this is what I'm after. Well, I have the slope. If only I had an x and y pair that I could put into this line of best fit in order to calculate my y-intercept. Well, if you don't think too hard about it, if there's one pair of x and y that should go in that, it should be your average x and your average y. So if I do that, if I assume that my line of best fit should pass through the average x and the average y, then I have all the numbers I need. So to get my average y, I would have to take my sum of y and divide it by the number of numbers. I have my slope. To get my average x, I would need the sum of my x's over this value. So 460 divided by 6, 76.7. 40 divided by 6 is 6.667 times my slope of 1.289 is 8.59. I'm going to have to do the tiniest little bit of algebra here. I'm going to have to pop this over to that side and subtract it. So my y-intercept then should be 76.667 subtract 8.593, which gives me a value of 68.074 with the rounding. So what I've just figured out then, because I have a slope here and I have a y-intercept, is that the equation of my least squares regression line of best fit would be y equals the slope 1.289x plus 68.074. So I'm going to try plotting this on there for you. So to sketch a line, you have to start at your y-intercept, which is 68. So 68 is somewhere about here. Well, that's encouraging. It's nice and close to my line. Next thing I have to do is travel on a slope of up 1.289 over 1. Now that's exhausting. I'm never going to be accurate with that. So we're going to employ a little cheat that no one told you about in grade 9. I'm just going to pick a place out here. Let's pick one at random. Let's see there. What did I get? 12? So I'm going to let x equal 12. If x equals 12, then my y value should be 1.289 times 12 plus 68.074. All I did was pick a random spot out here and dump it in my equation. So if I finish that off, 1.289 times 12 plus 68.074 try that again. 1.289 times 12 plus 68.074 is 83.542. Now, what you've done there, and the reason this helps, is you've just created an ordered pair. 12 on the x, 83.5 on the y. Well, that's here, approximately. And the whole idea of a line is once you get 2 points, you can just connect them. So you're going to get a ruler to do this, but because I'm hiding under a table, there, just like that. All right, so there's something really satisfying about this calculation because I just went through an arcane amount of calculations, and at the end I spat out this monster, and then when I took that monster and plotted it on the graph, look at that, boom, right through the set. Isn't that satisfying? So you're going to be able to self-check your work on these questions. If you calculate a line of best fit and its y-intercept is here and the slope is doing that and the data is nowhere near it, you need to go back and revisit some of this work in order to make sure it works out. So now that I've got this done, I want to think about what this line tells me. So first off, at the y-axis here, with 0 hours of studying, a person is getting 68% according to this model. So what it's implying to you is that with no hours of studying, a student starts with 68. Alright, well that's good. And you just show up and you get 68%. I guess it's not just showing up. I suppose your like natural inclination for mathematics and your ability to absorb information quickly from watching these videos instead of studying, doing the work on your own, is going to lend you a 68. From there, we're going to add to your mark by adding to your study time. And what this number here is telling you, the slope, is that for every hour of study, your mark increases 1.289%. So this line is showing that as we go across here, the trend is that with no studying, a student starts with 68 and their mark increases by 1.289% for every hour that they study. Well, that's a great piece of information, and it is clearly the trend that's happening in the graph, but don't forget this number here, your correlation coefficient of 0.497. So you ask yourself, how confident are you in this trend? I mean, it's what the data says. But you notice this person out here, this person who spent 12 hours studying and got an 80. Well, so did the person who spent 2 hours studying. So there isn't a do this, experience that kind of relationship in this data. The line is showing you what it does over the data set, but the correlation coefficient is saying, careful, you can't just assume that this is true. This is a trend in the data, not a fact. This hour studying does not cause an increase in your final grade. There is a correlation, but not causation. And the correlation, in fact, is not even that strong. So while there is some evidence from this very carefully collected data set to suggest that more studying means higher grades, I wouldn't be wagering money on this or committing myself to 36 hours worth of studying in order to score 100%. So I have a second example of doing a least squares regression line of best fit for you. So I have a new data set comparing how the hours you spend a day watching reality TV affects your IQ. Now, of course, this is a very rigorous study, and I stand behind the results 100%. So here we go. If you can hit your fast forward buttons and get through this pretty quickly, here we go. So now that all that's done, we have all our summations and our standard deviations and our covariance and our correlation coefficient. We can go back to calculating the equations of line and slope, or calculating the slope of the line of best fit. That's what I meant. So the slope would be the correlation coefficient multiplied by the ratio between the standard deviations. So I have a negative 0.976 times 21.9 divided by 3.555. This means negative 6.022, and if I drop those numbers into my equation for a generic line, then I have an average y being 450 divided by 5. My slope is negative 6.022. My average x would be the sum of x divided by the number of points plus b. That would be 90. Let me jot that down. And 33 divided by 5 is 6.6. .6 times 6.002 39.746. Pop that over. So we have an equation for this line of best fit. Y equals negative 6.022 x plus 129.746. So if I were to plot this particular line, you just go look at my data set, and I'm going to find the y-intercept of 129. That's awfully close to 130, so that's somewhere around here. And then from that y-intercept of almost 130, I have to drop 6 for every x that goes by. Now, we did this before. That's going to be challenging to do, so I'm just going to pick a random spot out here. Okay, I got 10. So if I drop that 10 in there, Ten's a nice number to pick because when I do this multiplication, I just have to pop the decimal place over one spot. So that's a hint for the future. Save yourself some work. And if I put those together, I end up with 69.5. It's awfully close to 70. So at 10 hours of TV watching, I have about 70 for my line of best fit. Now look at that. Just fits right in there, right through the center of those numbers. Makes me happy. All right, so what have we learned from this very rigorous study on time watching TV versus your IQ? Well, it would seem that from this y-intercept that a typical person starts with an IQ of almost 130. Let me just jot that down there. So typical person starts let's be more precise, of 129.746. And then for each hour of reality TV in a day, it drops 6.022 points. How confident am I in that particular model? I mean, the dots look pretty close to the line, and that's not enough though, is if you looked at that last graph in the last example, those dots didn't look too far from the line either, but that correlation coefficient was somewhere around 0.47, and this one is close to 0.97. So with a correlation coefficient like this, with one this high, I have evidence that this line, this trend, is highly reliable. And if you were to look back at the other video, the reason that that's happening is that there were 3 different hours of studying that led to a mark of 80%. If you look at this particular data set, there are 2 100s that show up, but they are right close to each other. They're not spread out across your data points or across the range of your X. So when you look at these 2 data points in there, they're somewhere between 4 and 6 hours of watching reality TV. So the fact that you're not getting repeats and that there is a clear decline in this number as this number increases, you get this solid correlation coefficient. So as far as confidence in these results, I'd say I was fairly confident that the amount of reality TV you watch does in fact cause your IQ to decrease at this particular rate per hour.